Hey folks, I've got a final example for simple harmonic motion. I've written down a quick summary too, which you're free to copy. We're either trying to find A as a function of x or alpha as a function of theta. In either case, the coefficient in front of the x or the theta will be negative omega squared, and then we can use omega to find the period of oscillation of the system. And then I wrote a summary here. If the only torque if the only restoring torque on a system is gravity, then you can use this equation down here. That's the period of a physical pendulum. Now, again, that's a big if. Only if the only restoring torque is gravity can you do that. Well, what if you don't have that situation? So that is the example that we're going to do. So imagine you have the following situation. You have a plank hanging from a pivot at the top, okay? And then it's next to a wall. And you have these attached with a spring of spring constant K. And let's say the spring is attached 3/4 the length down from the pivot. And of course, the bar has a mass M and a length V. So we got an M, I'm sorry, and a length L. There we go. All right. So what would the period of oscillation be for this system? Okay, well, we can't use this. We can't use the period of physical pendulum here because you've got more than one restoring torque. You do have gravity trying to always bring it back to equilibrium here, but you also have the spring trying to bring it back to equilibrium. So how are we going to figure out the period of oscillation of the system? Well, we're still going to use this idea. We're going to find, in this case, alpha in terms of theta. And whatever's in front of the theta is going to be omega squared. Then we have omega. We can find period. Okay. So what we're going to do is we're going to imagine that I pull this out a little bit. So like so. Okay. All right. And then we're going to draw an FBD. So we have the spring, which I'll call F sub S, pulling basically left. You're also going to have gravity pulling straight down. We'll call that F sub G. And then you're going to have some tension here. I'll call it F sub T on the pivot. That tension force will not cause any torque. So then what we're going to do is we're going to figure out all these forces perpendicular and parallel to the rod. So I'm going to draw another FBD. So here it is. Okay. Here's our pivot. Okay, so we got mg, and we're going to have two components of that, right? At the center, we're going to have mg sine of theta, and then we'll have this, which would be mg cosine of theta. Okay, now by the way, the theta would be from the vertical. Okay, well, then you're going to have the spring force, which would be force spring cosine of theta. So think about that for a minute. If you would agree that this angle is theta here, that's also this angle theta there, and we want the adjacent leg, which is cosine. And then you would have actually a little bit of spring force pulling up. That would be force spring sine of theta. Okay, so there's our components of the forces acting on the rod. And again, of course, we have the tension force, which is not going to cause any torque. So this isn't causing torque. Neither is the spring force sine theta causing torque. Neither is mg cosine theta causing torque. So the only two causing torque are these two here, and they're both pointing in the same direction. And by the way, we've displaced this counterclockwise. Both these torques are clockwise, so they're both going to be negative, opposite the displacement. So if we do net torque equals I alpha, what do we have here? Well, we have mg sine of theta times L over 2, negative, okay, plus negative force spring cosine theta times 3/4 L. And that all equals I, which I'll go ahead and put that in. For a rod at its end, it's 1/3 ml squared times alpha. Okay. Now, we have some work to do on force spring. Okay, as you might recall, the force of a spring, the magnitude of it is kx. What's x? How far has this thing been stretched? Well, then we need to do a little geometry. Okay, so if you imagine, oh, and by the way, I made a mistake, not a big mistake, but a slight mistake. This force spring cosine theta, that should be down a little further, 3/4 of the way. So if you would change that, force spring cosine theta. Okay. All right. So how far is this stretched? Well, I want you to imagine a triangle. It looks like basically like that. Okay. So I'm going to redraw that kind of by itself over here. Okay. So here's our angle. Here's our right angle, approximately. Now, this is 3/4 L. This is X. That's how far approximately the spring is stretched. Now, we're going to do the next several steps. We're going to do a lot of small angle approximation stuff. If this angle is small, then these two sides are almost the same because these two angles are almost 90. Well, this one is 90 and this one is going to be really, really close to 90. Okay. So this side is roughly 3/4 L. It makes a little isosceles triangle. Well, what's X? Well, X is approximately 3/4 L sine of theta. Okay, so I'm going to make that substitution down here first for X. So then we get negative mg sine of theta times L over 2 minus k times X, which is 3/4 L sine theta times cosine theta times 3/4 L, okay, equals 1/3 ml squared alpha. Okay, so we're getting a pretty crazy equation, right? Now I got to do some more small angle approximation stuff. As we learned in the previous videos, for small angles, and we roughly said 10 degrees or less, sine of theta is roughly equal to theta. What about cosine of theta? Well, what's cosine of almost 0 degrees? Well, pretty much 1. Okay, so I'm going to make those substitutions in here. Everywhere that I see a sine, I'm going to put theta. And everywhere I see a cosine, I'm going to put a 1. So then we get negative mg times L over 2. Sine of theta becomes theta. We got minus. Now I'm going to do some combining of terms here. We got 3/4 L times the 3/4 L. That would be 9/16 L squared. We have that k sitting there. We have cosine theta, which becomes basically 1, and we have sine theta, which becomes roughly theta. Okay, equals 1/3 ml squared alpha. Okay, well, we're really close here. We want alpha in terms of theta. So basically what I need to do is get alpha by itself. Okay, now it's a little algebra here, but we're pretty much there. So alpha equals, so I'm going to put the theta way over here. I'm going to factor it out. So I'm going to put the negative out front as well. And so what do we get? Well, our first term is that, which is mg L over 2, plus we have this term, which is 9L squared K over 16. And that's all divided by this term, which is 1/3 ml squared. So now we have it. We have alpha in terms of theta. Okay, now I'm going to do a little simplifying here, okay? But again, now we're leaving physics and we're just doing some math. So let's see, can we cancel anything? Well, it looks like one of the L's can drop out, right? So I'm going to drop this L and one of those and one of these. And then I'm going to multiply everything by 3 times 16 is 48, okay? So then I get a 24 mg plus 3 times 9, a 27 lk, all over, multiply the bottom by 48, I get 16 ml. And then that's times theta. So this whole crazy thing is omega squared. So the period of oscillation here would be 2 pi square root the reciprocal of all that. So you got your 16 ml over your 24 mg plus our 27 lk. And I don't think there's any simplification we can do beyond that, okay? So that is our period of oscillation of our system. Now, before you go, I do have one more highly important note that you're going to see in a couple of your problems, okay? So let's say I take this same situation, but now I turn it horizontal. So I want you to picture the rod horizontal. You're pivoting it at the end, and you're putting the spring like somewhere here, and it's attached to the ground, let's say. And then I ask you to find the period of oscillation of this guy, okay? Well, if you displace this thing slightly from equilibrium, okay, you're going to get your spring force, okay? And you're going to do roughly the same thing, no matter, depending on the fraction of L you got here, you're going to do roughly the same thing you did here. You're going to figure out what's X, how far that spring gets stretched, and then you're going to have a restoring torque like this, okay? And you're going to basically do the same thing. What about gravity, though? Okay, well, that gets a little trickier, okay? So if you do gravity, it's going to be here, right? And there's going to be two components. But now this component, assuming this angle here is your new theta, this will be mg cosine of theta. And so your restoring torque would be negative mg cosine of theta times L over 2 plus there's going to be the spring torque. Okay, so I'm not going to redo that, but it's basically going to be the same idea as this. The only thing that may be different might be the whole 3/4 L thing. It just depends on what fraction you have for where this spring is attached. And then that equals I alpha. Okay, now in this term, you're going to have your sine theta, which is going to turn into theta. What about in this term? Okay, well, all you have here is you have a cosine theta. Now remember, we're dealing with small angles. So for small angles, what does cosine equal? Cosine of the angle roughly equal? Well, it roughly equals 1, which means this torque doesn't vary much. It's roughly constant. So when you go to find the period of oscillation here, there's not going to be, and I'll write, there'll be no theta in that term. Meaning this torque is constant approximately, which means it's not varying. So when you go to find your omega, that won't factor in at all. All it's going to matter is what's over here, because that's the only term you're going to have a theta in. And so when you go to find omega, okay, it's whatever's in front of the theta. All right, so omega squared will be in front of your theta. You're going to ignore the torque caused by gravity because it's not varying with theta, whereas the spring force is significantly varying with theta. Okay. So that will come into play on a couple of the problems that you guys are going to be assigned to do. I hope that video was helpful, and thank you very much.